share the screen and then we can get started. So I guess before we start, I mean, it's good to have a very quick review on that, because I know the probability thing is the baseline of what we are doing today, right? Just I will spend at most 5 minutes to review what we have said, right? So probability is simply the way to quantify uncertainty in the future, right? We try to give the idea. We say this event A is more likely than B. How more likely? How so? To quantify that, right? The way we do is quantify that is we know to quantify if things can be repeated, right? From the data, then we can judge how likely they are, right? That is the idea of what we call the relative frequency, right? So we express probability, right, in terms of a fraction. So it's already a thing that comes from between 0 to 1, right? That's the idea. And if we want to extend ourselves from the data, right, to a more general idea, and we rely on some math tools, right? So we need to learn some axiomatic definition, right? So we learn the idea of intersection, union, and complement, right? Which are and or not, right? And then after that, we go through what is mutually exclusive, what exhaustive, and what is partition. And by understand partition, then we can define what we mean by probability, right? Probability must be a between 0 to 1, right? Remember, probability is a function, right, which give us from event to number, okay? And this number must be between 0 to 1. And later today, we learn random variable, okay? Again, it's also event to number, okay? But you will see why they're different, okay? They're both function from event to number, but here is slightly little bit different. The axiom 2 require you know the why is some echo? It's weird. There's a the sample space must be 1, right? And the partition of an event, right, is an event is mutually exclusive, and that end up is you can calculate the probability of the sum, right? Will be sum of the probabilities. So that is what it means, right? Then after that, we have complement rule, right? The complement and itself, the sum must be 1, right? And then we have addition rule, right? Is extension of axiom 3. If they're not mutually exclusive, add them, you have to subtract the intercept. And then we have the total probability rule, right? Probability A will be A with B, and the one without B. Okay. And after that, we define odd ratio, which is essentially an alternative way to talk about probability, right? The probability is from 0 to 1. Odd ratio is it will be from 0 to infinity. Okay, so that's another way to express the same thing. Okay, so there's no difference from probability, but this is the alternative way, and very often we use it in the casino or betting industry. So and right, because odd is easy to understand. 1 to 1 is like, right, it's the most the fair one, right? And after that, we go to the what we call conditional probability, which we'll define as A intercept B over B, right? Because A can be decomposed into A with B and without B, but the one without B is not relevant, and you have to normalize it because it must be 1, right? And after that, we just convert this to multiplication rule, right? Just multiply, right? And you come be this statement, you multiply both sides by a denominator, right? The multiplication. And you combine the two rules, give you this the rule that we use for the base theorem for the denominator. Okay. And before we go to the last theorem, this is the independence, right? Independent is saying that whether A happen is number B, B happen number A, and this will be used when we talk about do sampling, right? Because we want to say each sample is independent, right? And in the other words, you can do multiplication, right? So you can consider them separately, right? Without worrying about one interfere with the other, okay? And we'll use this as well today. I mean, so this is very important concept we'll use today, okay? And very lastly, the Bayes theorem. Do remember this is the formula that you try to update, where your initial information, we call prior, is the probability A. And now you know B has been true, that you update, right? A is probably you go to say doctor. A is the doctor think you have the disease. And B may be a medical test, can be positive or negative, right? Based on this result, the doctor will update how likely that you got the disease or not. So this is the standard thing actually you do every day, right? So every day, right? If you have girlfriend and boyfriend, right? When tomorrow is today, like it's a Mid-Autumn Festival, right? How he spend the time is with you and with his or her family, right? Which one's more, right? Then you can update your belief, right? Whether there's a diamond today or no, or there's a gold today or no, there's an expensive handbag today or not, right? Then you can update your belief about your partner, right? So that would be the thing, right? So that is the idea. And then I think we learned, I'm not going to repeat because I think you do the assignment. When you do the assignment, then you understand whether you know it or not, right? And you can talk with your classmates, or you can ask the TA if you have any query on the assignment, but it shouldn't be too much different from the example we have seen. So if you confuse, consult the example, then you will, okay? And right, since you have I mean the notes, then probably you also have more examples you can look at, okay? So I'm not worried about that part. So lastly, we have counting, right? And the principle of counting is just multiply, right? And permutation is a special way of multiplying when you try to draw n ball out of n possible balls, and all that matters is the permutation. If you try to draw out ball of n balls and the order doesn't matter, then it's combination. And the combination doesn't seem to be related to probability, but indeed that is something that are closely related to when you toss a coin, right? Toss a coin, and you want to see how likely that you get exactly two tails or exactly two heads, and that actually rely on combination, which we will see at the end of today's class. We talk about binomial distribution. This is the one that why we talk about this. Okay, so we give the foundation for that. But okay, so I hope you don't have question, but because that's just a review. So we quickly go into the thing we actually that matter, right? That is the random variable. Okay, so why we want random variable? Okay, the idea here, what is it first, right? It is basically say each outcome I give a number. Okay, and you may ask, there's no different from probability, right? Probability also event, I give a number, right? But number has to be 0 to 1, right? But now we are not really giving a probability, but instead we call an event, we just give label to number, okay? The label can be numerical number, right? And the way you can consider it is some kind of measurement, right? We try to measure our event using number, right? Say suppose asking whether today we are How is it very hot, not so hot, cool, cold, somewhat like that, right? Categorical. But sometimes we really want to have a measurement, look at the temperature, right? And this is sometimes we do because to measure things, right? So we use number to represent outcomes. And what kind of number you can use is called a support, right? And it's like the sample space, right? Sample space is what are the event, right? Support is what are possible number for the random variable. Okay, so and let me illustrate the example. Probably is a little bit abstract. The support can be discrete and continuous, which you immediately see later very soon. So what is the discrete? Is like counting number 1, 2, 3, 4, 5. You can count them. Okay, you imagine number of customers arriving at the store, right? Number of product the customer buy, right? That is an integer. Okay, so for example, you have a coin toasting exercise. You toast a coin. The outcome is either head or tail. Okay, and this is not a number, right? It's head or tail. So how are we going to use a random variable and to simplify the sample space, right? And we can, a meaningful one would be number of head. Of course, you can do number of tail as well, but the same. Number of head, then it means that H will be 1, tail will be 0, right? If you use number of head, right? So when have H, we will just write 1. When we have tail, we write 0, right? Just like you have an assistant to look at the random experiment, look at the outcome. When it's head, you record as 1. When you have tail, you record as 0, okay? So basically, you just like transform what you observe into number, okay? So here you have only 2 choice. So the support is 0 and 1, okay? And now we give the graphical representation. This is called the random variable. It's saying that for any event from the sample space, I give a number in the support, okay? And remember, this is the function. So you just like give me an outcome, I give you a number, okay? So that is the concept. And it will be immediately clear why this is a mathematical convenient object, okay? So look at this example, okay? We just do the coins toasting 2 times, okay? And from the principle of counting, actually you know that 4 outcome, right? Because you have head and tail in the first time and head and tail second time, right? 2 times 2, which is 4 outcome, right? Because we have head, tail, tail, head, tail, tail, okay? So, and let's see how we try to record this example, okay? Suppose we only care about number of head, right? In that case, when we have head, we record as 2. We have head, tail, or tail, head, records 1. And tail, record as 0, okay? And in that case, the support is 0, 1, and 2, okay? And by doing so, okay, what I'm actually doing is we are collapsing the sample space from 4 total outcome to the random variable to only 3 outcomes, right? And why we do that would make sense is we are going to reduce the number, right? Imagine, suppose we toast the coin 10 times, okay? And how large the sample space is 2 to the power 10 is almost like 1,000, right? I mean, to be exact, it's 1,024, right? And that means it's a huge number, right? But if you just count the number of head, then you have only 0 to 10, only 11, right? From 1,000 to 11, it's a substantial reduction of the complexity of the problem, right? Especially if you don't care, bless you, especially if you don't care, right, about the order, right? In this case, right, look at this, 0 to 1 and 2, right? And here actually head, tail, and tail head, we don't care about order, right? It will be equally meaningful to do this reduction if we don't care about the ordering of appearance, right? Of course, you may ask, okay, random variable is just assigning number, right, to outcomes, right? That's why I add another slide here, right? just a new slide, but it's technical, right? We can assign 1 to HH, 2 to HT, and 3 to TH, 4 to HX. That's fine, right? Because there's one number variable set, right? Just assign number, right? But is it very meaningful? Probably not. Unless they were meaningful. When meaningful is we're doing a casino, HX give you $1, HT give you $2, TH give you $3, HX give you $4. Then they will be meaningful in that case. In most cases, this doesn't really meaningful. Okay, so that's why when we try to put number to outcome, we use the one that's meaningful, right? So that is the idea. Okay, is that clear? So this is the way that I collapse it, right? It's HX go to 2, HT and TX go to 1, and TT go to 0. Okay, so that is what we call random variable. Okay, now we have discrete, and it's often a lot of cases are discrete. Okay, we count numbers, right? Counting, but sometimes you can't count, right? If you try to count decimum number from 0 to 1, you can't count it, right? I mean, there's no way you can count from 0 to 1 if you try to count the decimum number, because there are infinite number of them, right? There's no way, because for every 2 number you can give, I can give halfway. There's always a number. You can never reach that, right? That is the paradox of infinity, right? If you try to look at the YouTube, there are many videos tell you you can never say you can never walk to the end of this. Okay, I can never walk to the end of the wall, right? Because why? Because to walk there, I have to walk through the midway, right? To walk through the midway, I have to midway, so on and so forth, right? There's a paradox of infinity, right? But we know if you learn calculus, there's no problem to understand that part. But since we are not mathematics class, so we just say infinity will still work for our stuff, and we will kind calculus to do things, to do properly. But this is not math class. We'll just tell you how principle we can do that. Okay, and but since everything in discrete, in the intuition we carry to the continuous, so we just tell you the analog. Okay, we will not explicitly do calculus. But probably you ask why we care about continuous, because money is the best model by continuous random variable or stock price, right? Because the thing that you can consider is like anything is possible in between, right? You give me 2 numbers, anything in the middle is possible, right? You can't count it. Okay, so the example, look at the temperature, right? The temperature from, okay, is always any positive or to be above absolute 0 is feasible, right? So this continuous. Another one, probably stock market, right? Stock price, right? From 0, right, to any positive number you can go, right? So the sample space, or what we call the random variables, like this, right? So you can imagine the stock market is a very complicated object, right? We have many stocks, right? And that's every day we do, right? To describe how the stock market works, we don't tell individual stock, right? It's hard to say, because I think in Hong Kong we have around 2,000 stocks, right? It's very difficult to describe how they work, right? So we collapse everything into a single stuff, which is the index, and to describe that, then it's much easier, right? Instead of saying this stock go up and this stock go down, right? Then we just use a particular number to represent the data, right? That's actually what we do, right? What we call summary statistics, right? And we collapse the data into one number, right, to represent, right? So that is the thing we care. Is that okay? Why we want to focus on random variable is to simplify our sample space, okay? And to collapse into number, the reason is we know how to handle number, okay? And since we learn from our primary school, and high school, right? We learn how to do them. Okay. And so let's get started with the discrete random variable. And I do need to warn you, this part will be very mathy. We will have a lot of definition. Okay. So just you need to understand those. Will be a lot of information there. I will not show the proof. So just simply you need to understand what they are, and can be boring. Okay. So what we have is, before in the last class, we have sample space, event probability, right? And for each event, I will tell probability. Okay. Now, instead of event, I have random variable, right? So if discrete, I can count them, right? X can be what, say 1, 2, 3, 4, 5, right? Then this function, okay, is trying to tell me, you give me the number, I give you the probability. Okay, that is called the probability mass function. Okay, and in other textbooks, sometimes they call PF or PDF. Okay, so not the PDF you use, but this is the standard name. But this is the one that is the way you describe random variable, right? Because you tell me for each number it's possible, then give me the probability. Okay, this is the way to describe. And there's another way, which probably not so natural in this context, but will be very natural when we talk about continuous. Okay, so later you will see our idea extend from discrete to continuous actually through this object. Okay, this object is called the CDF, is cumulative distributed function. Okay, so basically, by definition, it's not complicated, but what it said is the probability less than or equal to a number, right? So suppose you give me f of 2, is probability that the random variable is less than or equal to 2. Okay, so that's why it's adding up what is before it. Okay, so sometimes it's called DF. Okay, so very abstract, the two definition. So it's good to go to example to make it very concrete. Okay, we'll illustrate by example. Okay, that is standard way you learn math. You always start from definition. You try to understand what they are doing, which I told you. Then you look at the example, and then we'll do some exercise as a class. I mean, when you go home, then you understand what exactly it is. Okay, and let's see the example. We're doing all the coin toasting, right? So let's continue to do that. We toast a coin, which we assign number of head is our random variable. Okay, so that means that what we are doing is the following, right? So we have, when we see tail, that actually is 0, right? Because number of head, right? And when we see head, right, that is 1, right? And I claim this is a fair coin, so both outcomes are equally likely, right? So remember that means that fair coin means the following, right? Probability of a head and probability of tail is 1/2, right? So that's why we have 1/2 here and 1/2 here, because probability head is 1/2, right? So that's 1/2. Probability tail, right, is x equals 0 is 1/2. So that's how you get 1/2 for the p of x. Okay, is that clear? Okay, you just now I call tail and head a number, so the same thing. Is that clear? The next will be the spec f. Okay, spec f. Spec f. So this spec f is probably slightly not easy to see, but remember f is what? F of 0 is what? Is, if you define properly, is x less than or equal to 0, right? So, but x can only be 0, less than or equal to 0 is exactly probability equal to 0, right? But x equal to 0 actually is p of 0, right? Which is 1/2, which is exactly the above, right? Because this is p of 0. Is that clear? Why you have this? This is 1/2, right? This is immediately come from this one, right? Now, let me finish this one, then probably you would have more clear why this is 1, okay? What's f of 1? F of 1 by definition is probably that x less than or equal to 1, right? That's what it means, right? And you know what can be less than, or maybe I use other color, this is a little bit too not dark enough, probably the back cannot see. Maybe it's another color. Is it better? So f of 0 is probability x less than or equal to 1, sorry. Okay. And that means what? X can only be 0 and 1, right? Then just mean the following. X equal to 0 plus x equal to 1, right? And this is 1, this is p of 0 and p of 1. And both of them 1/2, that's 1. All right? And actually simply means if you graphically, it's just this guy, you go up and add everything up, right? From F, you go to the P and add everything on the back, right? Basically go up and turn left, right? Collect everything there, right? So don't worry, graphically we'll see in the next slide. You will see how that's very graphical, okay? Although in a table form, it still seems to be a little bit tricky, but when we look at the bar chart, then everything will become very visual. Is that okay? So don't worry, we have several more examples. Make sure that you understand, okay? Because this is the fundamental concept of random variable, okay? I know for those QFN students, it's very slow, but we have to cater the most of the average of class, right? So we left no people behind, so have to and just to make sure if you, because of the this is a basic class, so if you want more exercise, it's very easy. Go to online, you can find many complicated, very difficult exercise. So I'm not worried about you if you're a QFN student, right? So here you have the case of pros and cons, right? And number of head, right? Only 0 and 1. So I try to draw this P graph, only 0 and 1, right? Since they're equally likely and 1/2, so that's why we have the red and the blue bar here, right? 0 is 1/2, 1 is 1/2. I hope you don't have any problem with that guy, right? Now, how to redraw this big F? Okay, the big F is not complicated, right? Remember this F, big F, right, is simply asking acting by the P, okay, the big P. So 0, there's nothing before 0, so that exactly copy. And 1 will be simply you go here and add that back. So that's why it's blue plus the red one, right? You're just stacking, okay? Keep stacking. Okay. Later you see when it generalized to more than 1x, you don't have problem. Okay. So that's the idea. I hope it will make sense graphically, just basically stacking things. Okay. You imagine just a Lego. You just have it here, you stack, okay? And one more, they keep stacking, okay? You will see in the next example how this thing can be done, okay? Is that okay for the moment? Okay. Let's see the example. I think the example help us a lot. Okay. Here we have another one. Remember the example is we toss a coin twice, right? Then we only count number of head. Okay. And what does that mean? Okay, number of head. Let's do it. Okay. Here I have head, right? How many head I have? 2. So this is exactly mapped to this guy, 2, right? And I have head, tail, and tail head is exactly 1 head, right? So map to 1, right? And what will mean tail? There's no head. This is 0. Okay. So this is what the X would do, right? X would do. Now, let's go one by one. Okay. What is this guy, right? This guy's what? This guy's P of 0, right? P of 0 is probability that X equal to 0, right? X equal to 0 is indeed probability that you have TT, right? And TT is what? It's a fair con for outcome. Each outcome equally likely. So it's 1/4. Okay. That is how you construct this table. Okay. I'm going to illustrate one more. Okay. On the blue one, right? P of 1 is what? That is probably that X equal to 1. That is probably that we have HT or TH, right? I mean, of course, you should do union if you to be a proper, but it's okay. And they're mutually exclusive because you just add them up, right? But anyway, just one half, right? And lastly, P of 2 will be probability X equal to 2, right? So that is probability that which is TT, right? So you have 1/4. Okay. So that's how we get the answers for the entry of the P row. Is that clear? So for the F row, I just do the first few. Should not be difficult. Okay. Let me do this. Y is 1/4. F of 0 is asking the probability that X less than or equal to 0, which is exactly X equal to 0, right? And this is P of 0, which is 1/4, right? Because less than or equal to 0, we just only have 0, 1, and 2, right? So that's why it's 0, right? And let me do the other one. I will left the F equal to 2 to you because I don't want to be too spoon feeding to you, right? This one, less than or equal to 1, you have 2 choices. You have 0 and 1, right? Because we have 2 things. X equal to 0 or X equal to 1, right? And this is I just being lazy. 0 plus P1. So it's 3. So basically, this is how you get, right? Just go up, right, and add, right? Add 1/4 plus 1/2, you get 3/4, right? I'm not going to do the last one because I expect you should able to do that. Okay. If you don't, you should able to see why this is equal to 1. Okay. If not, then you don't understand. If yes, they don't understand. Okay. Is that okay? So this will be serve the foundation when we talk things later, but this is very important. Okay. Now let's do the graph, because for those of you who are very graphical, you will see the shape start to have some meaning. Okay. You see this one, it's 1/4, 1/2, and 1/4. Okay. And this looks like the bell shape. And indeed, later you will see when n is large, okay? Actually, sorry, I mean I told you many con many times. This will look like a bell, okay? And that's why we use normal. It's because when n is large, it's become a normal. And bell shape will be the way we do. That's why we always do bell, right? But we'll talk about this when later, okay? But this is a bell shape, okay? And how you come from P to F, right? And that's not difficult. Just do Lego. You have this Lego, how you get this up, right? You just stack 0 to 1, you get this one. For the 2, you just stack everything there, you get 2, okay? I hope the color would help you to understand what we're doing, right? I mean, of course, we start getting more difficult because we're getting more mathematical, okay? But the idea is not complicated, okay? And we'll explain why we need that at the end of this class, right? Because all this will be very useful. And probably you should see, although I only show from P to F, you should be able to do the other way around, right? From F, you can do P, right? Because just Lego, right? From here, you can do here. From here, you can also go back to this one, right? We go to left to right, you should be able to go from right to left. That shouldn't be an issue. So they are the same, okay? Two is two sides of the same coin, okay? Any way would be good, okay? And you will see for discrete, this is better. For continuous, this will be better, okay? Later you will see, probably next week you will see why, okay? But now we just learned the two ways to represent the same thing, and that is the goal, okay? So we'll finish this example and then we'll break, because if you don't understand, you can ask me, is the right time? So we have a sample space, S, okay? And that go from 1 to 6, okay? And naturally, I will use the face of the die, the value, as the random variable, right? We have 6 numbers, okay? And this is a fair die, then it's 1/6 for each number. So P of X is 1/6 for each one, right? And it's able to see the big F, why we go from 1/6 to 1, okay? And I hope you will be able to see. If you don't, then ask me during the break. Hopefully I can solve your problem, okay? And the graph of P will look like this, which is unsurprising if you know the bar graph. That is the way you present the data. And if you are QFN student, please note that this is not rigorous enough. You should do it this way, okay? You should do a line and dot. If you are non-QFN, it doesn't matter, okay? But this is the way you should write. And because that's why if you go to stat, they will require you like this, okay? This is the stat. You will require to write in this way, okay? And for us to write this is also fine for B school, right? But if you are from QFN, please notice this is not complete. You should give the step function, okay? Somewhere in the middle also would define properly, okay? Because that one we don't define in the middle, right? But actually this is how it defined. It's defined as the left continuous, okay? Very technical, okay? But if you're QFN, you have to be careful, okay? But since you're B school, okay, most of B schools, then this will be good enough, okay? But do note that this should be the way if you go a little bit more careful, okay? But that's fine. I mean, we are not that crazy, okay? So after the break, we will talk about expectation, variance, and that is how we connect ourselves from topic 1 to topic 2. How probability related to summary statistics. Okay, so let's have a break of 15 minutes. I will open the U reply. So let's. Oh, I can do that. Okay, that's good. Question you don't want to ask me, you can leave me when you reply, I will answer. So I will end the and the you reply, okay? Let's see the result. Okay. Three of them is exactly 3. Yeah. If I say more than that, will KDE in Excel, what mean by KDE? I don't know what KDE means. I guess you mean whether Excel add-in. If we don't cover in the class, then it's not. I guess that's what it means. Yeah. Happy Mid-Autumn Festival as well for all of you. Oh, just to remind you, today is Friday. For those who don't know today, it's okay. Okay. Again, today we are more diverse understanding. Rainy, yeah, fine. Yeah, fine. That's fine. I mean, today is okay. We have some distribution over this. Okay, that's fine. I mean, that's good. Yeah. So I think most of you have good understanding. Is it the key point we cover in lecture? Let's see. I don't know. So what's the answer then? So what the here is McDonald's deliver take away, and Starbucks sell coffee. What is the church sell? Okay, I don't know. Oh my God. Okay, that's good. Okay, that's good. Yeah, because if you understand Cantonese, then understand. If you are not from local, then you understand the joke. Okay. Yeah. Okay. I think it's a good joke. So today's slightly more difficult. That I can see some people feel a little bit fall behind, or it's okay. Okay. I let it joke. Maybe you can tell that in the CC weekly assembly. But anyway, so during the break, I talked to some of you, and one question that actually have that from the audience today is the assignment. Some of them said a lot of copying for the question 1 and 2, and I told them you can just write first few terms and write ... and then write the last term to save your effort. I mean, you just demonstrate you know the thing, right? You don't have to make yourself do a lot of copy. Okay, as long as you as long as you convince the TA that you know, then it should be fine. Okay, if you cannot be, the TA cannot be convinced, he deduct your mark, then you have to talk to him, show him your understanding, then it should be fine. Okay, because I think we're very liberal. We are not going to be very strict, right? But for the exam, I mean, try to give more detail possible, because I cannot possibly ask you what do you mean by that, right? We just can give you benefit of doubt, but beyond that, we cannot really. That's the limit of how liberal we can do. Okay, so try to write as detailed as possible in the exam, but for the assignment should be fine. Okay, now what we have is the expectation. Okay, and expectation of random variable is exactly same as the mean if we do the experiment many times. What does that mean? Okay, if we have a random experiment, okay, that is behind the random variable, right? Suppose we're talking about tossing a coin, okay, once, right? Then we record number of head is either 0 or 1, right? And if we repeat this for 2 million times, right? If the coin is fair, we should expect 1 million of head and 1 million of tail, right? And each time you see a tail, you get a 0. You get a head, you get 1, right? So you have a bunch of 0 and a bunch of 1 as your record data, right? And you expect 1 million will be 1 and 1 million will be 0. Okay, what is the average of this data? Is 1/2, right? Because you have 1 million 0 plus 1 million 1 over 2 million, right? Because you 2 million of toes, right? So which is 1/2, right? And this will be exactly same as what we call expectation. expectation is a weighted sum or weighted average, is you get value of the random variable times the probability. Okay. Why is weighted sum? Because you can simply divide it as sum of the p, right? Sum of the p is 1, right? So you don't have to divide, right? So it's a weighted sum or weighted average, right? So usually we will call this mu. This is a mu, Greek letter mu, and x represent the random variable. Okay. Just to remind you that when I have capital letter, x is a random variable, and I have small x is a number. Okay. Big X is the random variable. Okay, it's a function, and small x is a particular value like 1, 2, 3, 4, 5. Okay. Here means expected value of the random x is you look at all possible numbers and multiply it with the probability and add them up. Okay. We'll show you immediately what it is, but do remember what it is. The expectation means suppose we repeat this experiment many times. Every time we record the value, carry the average. Okay, but exactly same as this one. Okay, right. I think I explained in this here. We have explained that, right? Total second ones, and it's 0 and 1, and then we say it's 1/2. And actually, if you do 1 million toes, 500 million, it's 1/2 million is tail. Okay, so that is the idea of mean, right? So expected value is mean if you repeat this many times. So that's how we connect topic 1 and topic 2, right? In the topic 3 here. Okay. So the mean will be something we study a lot of time. Okay. Is that okay? So here the example, then how we use it. Okay. Expected value, right, is, look at the table, how we operationalize this is for each value of x, right, go to 1, just go from 0, multiply is p of 0, right, and let's multiply this, right, and then the next one will be 1, you multiply the 1, right, so it's here. Okay, add them up is half. Okay, and remember what's mean, right? Mean is the value in the middle, right? So it's exactly where, if you try to guess what is the next value of x, if you want to guess, will be say half. Okay, of course, probably not more meaningful because no half, but half is the thing that you will guess, the number, right? Not more, not less. Okay. So let's see, for example, roll a die, right? If you try to roll a die, right, you record the number, right? The mean is just 3.5, right? It's just every number of x multiplied by the p of x and add them up for each one. Is that clear? Is that clear for this one? Okay. So probably you would want to see how this thing collected with data, right? Here we just do one thing. We assume we know x, right? And we're probability, and we get what we expect, right? So this is, we come from the assumption, we get the mean, okay? But in reality, we do this reversely, okay? We will get a data, we get this guy, right? And we try to go back, okay? So we go in the data, we do reversely, right? But in the theory, we do in this direction. But data, we do backward, right? But later we see what we mean by backward. But in the next month, we'll talk about backward. But now we just go forward direction, right? We have the die, we know what's going on, then we get the mean, right? You can imagine, right? This is the distribution of income in a city, right? You have 1/6 of people get $1, 1/6 of people get $2, so on and so forth, right? And this will be the average income, right? Or if you pick a random guy from the street in this city, then that will be the 3.5, right? Will be the thing you expect the number to be. Okay. we can see now we have what we call the linear property of expectation, because expectation is just sum and multiplication, right? So with the sum. So that's why we have the following, okay? The first one said, if you multiply the random variable by A, okay, then you can just simply take A out, okay, and do it, okay? Probably you ask why we do that, okay? What's the purpose of this? Imagine X is the stock price, okay? And it essentially means we only need a model. We need to understand how a particular stock, okay, was an expectation of particular one stock, okay? If your portfolio have 1,000 stock, okay, A is 1,000, okay? You just need to focus on one stock and multiply 1,000 will be your expected value portfolio, okay? So you don't need to figure out what's expected value for one stock, two stock, three stock, four stock, five stock, or 1,000 stock. You just calculate particular one stock and multiply how many stock you have, then you're done. Okay, so this makes your life easier. Okay, you don't need to have you don't need to calculate a lot of time. The second one here means I have expected value plus a constant. I then focus on X and plus B. I can do the B later. Okay, what is the significance of this? You can imagine X is a stock, B is the cash, right? In the portfolio, there's some cash. Cash a constant, right? It's not going to change by any random thing, right? And that means that you don't need to your portfolio, the total value portfolio, it's just stock plus cash. You can separate when you calculate expected value. You can focus on the stock and just add cash, okay? And that makes life easy. Okay, this is the idea. Lastly, you can imagine combine in two steps, right? You have 1,000 stock plus cash. That's how you calculate. Is that clear why we have this? Formula is useful, okay? And later you will see how we apply that in example, but that will be very soon we'll talk about that. Is that okay? Why we have all this? Okay, the proof is here, but I'm not going to do any proof. Okay. Next, I mean, for QFN student, you should be able to understand this. Okay, should not be an issue. I mean, you should check it out and make sure that you get it, because this is something that if you go to stat class, they will just prove it. Okay, we're not proving anything. Okay, but shouldn't be difficult for you to do the proof. If you really want to know how I do the proof, you can check. I think I taught this class this is my fourth year teach this. Okay, you can check my first year and the first year I taught this class, I covered the proof. Okay, you can check the video at those days and they're there. Okay, but I don't think you will need it unless you really math thirsty. Now we have another one for variance, but the name suggests that is exactly the variance. If you repeat this experiment many times, you get a number. That's the variance. Okay, the same thing. So now you can see the formula I write is a little bit tricky. Okay, looks like a monster, but this is no different from the definition. Remember the variance, how we define is average square distance from mean. Okay, let me repeat the statement. Variance, when we learn, is called the average distance from mean. Okay, so here you can see here. This is distance from mean, the blue part, right? The blue part is from mean, right? And we have average, you have square distance, right? And is average. So that it means average distance from mean. Okay? And this operator, it just multiply this guy by P, right? Okay? E of whatever, it just whatever times the P, right? So that's the idea. Okay? Of course, if you go to QFN, they have to explain why this is true, but not our class. Okay? This is have to be proved. But the variance, okay, we will use sigma square to denote it as we do. Okay? But here I have a capital letter X to represent is a variance for random variable x. Okay. So there's nothing because you know how to calculate variance, right? So this example, how to calculate variance, okay? And we know the mean is 3.5, okay? So how can we do this? Let's show you one by one, okay? How I do this, okay? How I do that? So I go number by number. First, I go to I go to the first one. Okay. What I do is I take the number here, 1, right? And I subtract it from my mean, right? That's what I do, right? This is this term from the mean. And then I take a square of it, right? And then at the end, I would multiply 1/6, okay? And I repeat this procedure for each number and add up all the outcome for 6 steps, and that's the answer, okay? Of course, here I write 6 number. Of course, in the assignment, if you actually ask to do, you can do ... right? Just give me the first, second, and the last, then should be fine, right? If you want to be, you don't want to write that much. Okay, this is the variance, okay? Is that clear? Is that okay? Is that okay? So that's the variance. Now, here comes the another one. If you download earlier, there's one more formula, but I choose to take this out because I think that formula is only useful for QMS student. So I just take away the first formula, okay? But I will explain what is that formula for, okay? Let's focus on this formula first, okay? And I'll explain the last one later, okay? Don't worry about that. I'll talk about the first one, okay? So this one simply means if you have 1,000 stock, okay, your variance is not just 1,000 more, okay, but 1,000 square more, okay, because variance is square, the idea is, okay. So it means that in absolute terms, the variance is like way much larger, okay. So okay, so that is important. The second one, I think I have a typo in the one on the note that may be done earlier. There's no B here, okay? Otherwise, the same formula, right? So what it said is, you have a stock and plus a cash, right? This cash is not going to change anyway, so there's no change, right? So that's why you just focus on the stock variance, okay? Your portfolio has stock and cash. The variance of portfolio will be just variance of stock, okay? Is that okay? So make sure that you got the formula right, because if you download the earlier version, there's a left-hand side, right-hand side the same. So basically meaningless, right? So I don't know why I have this error, but it's there. Even though after many years, I don't know why I still have that error, but it's always there, okay? This one is very simple, right? Yeah, 1,000 stock and plus cash will be just A squared, okay? Basically, you just need to remember the last one, right? Because the last one is the thing you need, right? Is that clear? So we'll be using this all the time to make sure that you don't make a mistake for this one. Okay. And this is the one that I remove it from your slide. This is the formula. Okay. And this formula is nothing but a way to simplify our calculation. If you want to do proof, this is the formula that, or do calculation, this is faster. Okay. And this essentially said variance of a random variable is simply the expectation of its square minus square of expectation. Okay. And this is only useful for the proof or doing some calculation by hand. And since we are not using it in anything, so I just move it to the appendix. So the technical part, so that's why you don't need it. Okay. This is the mathematical proof why this is true. Okay. And if you don't like math, that's also fine. You can see this in action. I also change this to technical because I think you really don't need it for most of you. So that's why I moved technical, and that illustrates how you can calculate expected x squared and why these two formulas give the same answer. Okay. And since we don't really need it, so I just leave it there. Okay. We're not doing the proof. So why I need that? I mean, unless you do calculation, right? Okay. So if you want, you can just read it by yourself. Okay. And I'm not going to cover that because 90% of your classmates not using it, so I'm not spending time on that. If you still have question, ask me next class how I can explain to you. Okay. Or you can just ask the TA. Okay. So here I have some technical thing have to talk. Okay. But that is, you would think that is not very surprising. Okay. But this is actually useful for the future. Okay. So here is called bivariate random variable. Okay. So far we focus on single random variable, right? We just use one number to describe uncertainty, right? But you notice that in many cases, you want more than one random variable, right? Suppose my portfolio may consist of stock and bond, right? Or I have two stocks, right? And how can I do that, right? And that's important, right? That is easier to handle this, okay? And the way we do, which is also in the technical part, right, is we will have to consider the joint distribution, which is beyond the scope of our class. If you want, it will be covered in the 2021, okay? And by put them there, if you do QFN, then I mean you will have faced it again. If you are not taking the next class, that will disappear. Okay. So I just describe that. You can also have the marginal and the cumulative to describe what we want. Okay. But you don't need to understand this. What you need to know, I change it back to something we need. Okay. This is the slide we need, so please make sure this is not technical slide. This is a real slide. You should know. Okay, is assuming that we are able to describe a two random variable, actually more than that, we can calculate expectation. Okay, and the good part is there's a rule that when you do the add, you can just separate them. Okay, you don't need to consider that they are the same, because of the property of the probability. Okay, so you don't have to worry about that. That means that if you calculate, you have 10 stock and 3 bonds, then just calculate as the same. Okay, you don't have to worry about that. Maybe you buy the I bond, I don't know, the green bond. Yeah, so, but that is what it means. Okay, so you can separately calculate mean for the bond and mean for the stock, just add them up. Okay, so that is the meaning. Very soon we'll see application, why we need that. The other one is called variance sum. Okay, and let's do the following. If x and y independent, okay, variance sum is sum of the variance if they're independent. Okay, and we'll use this when we do a lot of proof in the sampling. So they are the same, so we don't need to worry about that. Okay, but probably you would say, right, maybe bond and stock is okay, but what about stock A and stock B, right? If stock A and stock B, they're related, right? So how you can do this? Okay, and that will be something that covered in advanced class. Will be, you need to care about the covariance. Okay, and this will be the formula. Okay, but we'll talk about this after the example. Okay, suppose you have two stock X and Y. Okay, and they are independent. Okay, and you can calculate if you do half of X and half of Y. Okay, then what's the portfolio return? Okay, and you can follow the calculation. I think it's very clear. And compared to a slide, I just add some step there. So now I think it's a little bit more clear compared to a previous slide. Okay, so it tells you how we do calculation. And if you do the investment class, I think finance 3000 class, they actually do all this for the whole semester. Okay, and one thing that will be important is this guy. I mean, it's out of scope, but you see this covariance important when you do investment, right? Because now we're not investment class, I just hint what we're doing, right? So the variance of your portfolio will be some of the variance of individual part, but you have the covariance, okay? So most investors don't like variance. You like high, mean, and low variance because variance are taking risk, okay? And you want variance low. So how you make variance low, right? You want this to be negative, right? The smaller the negative, the better, okay? So that's why people want to invest in cryptocurrency, invest in NFT, invest in overseas diversification, right? Diversification make this small, right? Rather than put all the eggs in the same basket, you put in multiple baskets, right? Then makes things easier, right? So that is the covariance idea, right? It's diversification, right? And do remember what the covariance means, right? Covariance negative means when one goes up, the other goes down, right? So they cancel out, right? So there's not much variation. But of course, these are all out of the scope of our class, but just let you know, all these can be learned. A lot of funny thing, interesting thing can go on, okay? But it's not the scope of our class, right? You just need to know the thing is blue and the thing is green, is able to do it, okay? Other than that, it's just for your interest and because you will learn anyway in the future. But I mention it because otherwise you don't know what you're doing, right? Okay, there's a lot of proof here, but I don't think I need it. So now, before we end today, we will talk about application of what we learned. Because you learn so much math, right? You really want to see how it put in action, right? And these are the way that you put in action, okay? And we learned the random variable. Why I learned that? Because they are actually turn out to be this kind of P function, right? The probability mass function. A lot of them actually very common in practice. We see many common distribution from the real world, okay? And the bell curve is something we know. And the binomial later you will see is a discrete version of bell curve, which often you also observe in the real world as well, okay? And later we see Poisson or hypergeometric, also very common, okay? And we'll cover the Poisson and hypergeometric next class, but this class will focus on the first three, okay? And later you will see all these are very common if you try to build a probability model, right? Because probability is what? About uncertain about future. If you want to build something to understand the future, that's what you do, okay? Now let's get started for the very first one, okay? The very first one is the most simplest, I guess most stupid, most boring one, which essentially said every outcome is equally likely. If n outcome, right? Because everyone's equally likely 1 over n, right? There's a typo in the original version. There's a 1 here. It should be xn. It's not. I think the typo in the 1 in your look. Just change it. Okay. And when we use it, right, is how number of head, number of tail, number of row in die. You may ask why we care about this. In the real world, no one is going to roll a die. No one is going to toss a coin. We don't care about those, right? And the question would be, when you use this, you will use this to in your understanding. If you don't know what's going on, okay? You know what the outcome, and you don't have a right model. Uniform is the right thing, okay? And we don't teach in this class, but you can start with this and use Bayes' theorem to update and keep updating. So that's why Bayes' theorem is very important, although we don't teach in this class, but this will be taught in the 4000 class, I think. And how you go from prior to posterior, keep updating. And at the end, that's how you learn. Indeed, that's how things learn. Remember, if you, several years ago, that's what we call the AlphaGo, right? AlphaGo was human in the Go, right? And how they train the AlphaGo. The beginning version is the AlphaGo study the human menu of Go and keep running the thing, and then he win, right? That's the Go deep learning. And he keep updating, right? But remember, after the first round, I think AlphaGo win. The second round, the human win. And the third one, that Google changed their method. It's not starting from human understanding. They start from scratch, ask two AlphaGo play with each other, and come up with the very smart system. That's what you do. You start with something stupid, which is uniform. You keep update. That's how we construct. If you, I mean, there's no FA student. When I learn, that's how insurance company learn the probability of a new insurance policy. Accident happen, as they learn, right? Because you don't know how likely that certain accident happen, right? But they say now after typhoon, I think at the beginning of this month, we know how likely that you get a flooding, you get getting some accident, then they update. Okay, this is a starting point of doing things. If you don't know what's going on, this is the natural starting point. Okay, and this is the PMF graph, right? If X is from 1 to 5 like this, 1 to 3 like this. Okay, so the more outcome is more spread out. Okay, and that will be the case, right? Now, I think now is go to the next part. Is called the Bunoni. That is really starting from something interesting. Bunoni, some of you who know mathematics, Bunoni is a famous mathematician and one of the fathers of doing probability. Okay, and Bunoni is very simple. It's simply posing a coin. Okay, but the coin need not be fair. Okay, can be biased. Okay, that means that I have head or tail, or we call success or failure according to the tradition. Success have probability P, failure 1 minus P. Okay, if P is 1/2, it's exactly tone coasting, right? And if P is 1 or 0, then actually there's nothing interesting to study, right? But anyway, we still allow that to happen. Now, what's the random variable? Same as number of head or tail. We use 0 to denote failure, X equal to 1 to success. Okay, so it's number of success as a random variable. Okay, so the support is 0 or 1. Okay, we just do ones. So the probability of 1 is P, probability 0 is 1 minus P. Okay, so what is Px here? Right, it's 1 minus P and P, right? That's very natural. Okay, and probably you ask, okay, what is the application of this? Right, this asking whether 1 or 0 is success or failure, right? Can be considered as the next customer come into my restaurant. Does he like spicy food or not? Right? That is the P, right? And P will be a fraction from historical data. How many customers actually like spicy food? Right? And probably ask why I care about this fraction, right? Because you would try to see how many spicy food, how much spicy food you need to prepare for a restaurant. Later you will see when the next binomial, that is something makes more sense, because only one here, right? You only serve one customer here, but next one you serve more customer, then you will see more. But here we just do once, right? And that will be this is the building block for the next one. But we start from the first one first, okay? Only one guy, we just draw an outcome from there, okay? Now, is that okay up until now? So here we will be doing something a little bit crazy, okay? Is we have write in this way, right? We will write the probability function in this form, okay? So remember here, what we have is X is either 0 or 1, right? P of X is either P or 1 minus P, right? This is the one, right? You may ask, why am I crazy right in this particular form? Okay. And I do have same question with you. When I first see this, I see, what? I mean, it's some mathematical joke. Okay. I think I spent at least because I don't internet that time, I think I spent like 1 week to figure out the answer. Okay. Later I'll tell you the answer, but let me show you why this is true. Okay. If you put x is 0, okay, p to the 0 is just 1, right? And 1 minus 0 is 1. So this is just exactly 1 minus p, right? And next, we have x equal to 1, right? X equal to 1, this is 1 and 1. 1 minus 1 is 0, so this is 1. So that's p. So let's get back to this one, okay? And why we need to write in this way will be clear immediately in the next few slides, okay? So just bear with me with this one, and you see why we have this one, okay? It's when later you will see, actually it's more natural to have this one, okay? You agree with me, this is more natural. And we don't do the proof, but as we expect, the expected x will p, okay? If you repeat this many times, p of them is 1, 1 minus p of them is 0, average is just p, okay? And this requires some proof, but the variance is p times 1 minus p, okay? And I'm not going to show the proof, okay? I will try to argue why this makes sense, okay? The proof is easy to prove, but I'm not doing the proof. So let me show you the proof why, let me argue why this is true, okay? This one, the variance, okay? Let's draw this guy out. P times 1 minus p, right? Let's use our high school math. When p is 0, this guy is 0, right? And p is 1, this is also 0, right? And if you learn this is a constructed function, it's a parabola, right? Actually, it's like this. When this is 1/2, this is 1/4. Okay? So let's make sense of this graph. Okay? If p is 1, what happened? Always success, right? It's always 1, 1, 1. There's no failure. So we're in 0. Or p is very close to 1, then it's always almost always 1 and only few 0. There's no variance. If p is close to 0, then it's always 0 and maybe few 1. There's not much variance. But when p is 1/2, you have half of them is success, half of them failure, right? Half some 1 and some 0. That is the maximum variance, right? So that is the idea. Okay, so that why this makes sense. But of course you have to prove it if you want to make it true. But we are not the math class, so this is given as a formula for you. Okay, it's okay. And okay, so this the graph looks like. If p equal to half, it's look like equal. If p is less than 0.3, that's less successful, more in this way. If p is more than half, it's look like this. Okay. Now, I guess the main thing is how are we going to use it? Usually we don't use directly. We use this one, which is called the binomial. Okay, which I think is easier. It basically repeat the contour thing many times, exactly n times. So we repeat n times, and n times, and it's independent. That's important. Each time, the result for this time doesn't affect the next time. Okay, and each time has a set of p. Okay, and we care how many success we have. Okay, that's why the success comes from 0 to n, right? Actually, same as the contour thing we have been doing many times, right? Okay, and now the question is, why the p is like this? Okay, why the p is like this? So because independent, right? Let me explain this one by one. Why you have this thing? To get success, the probability is p, right? To get 2 success, you will p times p. right? Because remember independence, right? If you have, I call success S, failure is F, right? I want the probability of success first and success second. Because they're independent, right? Independent means I can separate them, right? Because this is what independent means. This comes from independence, right? Independence. And this is what? First success P, second success P, right? Multiply, right? So if I want X success, so P raised to the power X, right? P success. And then if I want the rest of them to failure, it will be just 1 minus P times M minus X, because all the rest is failure, right? I found first X success and the rest are failure, right? And why I have NCX is because success, and failure is one way to do it, right? I can have failure first and then success, right? How many different ways to do it? It's NCX, okay? And if you don't recall why NCX, go back to the last class at the end of the slide. We call combinatorial with toes and con. Exactly 2 head is just for C2. It's just NCX, okay? If you get it, you get it. You don't get it, just remember the formula, okay? And that is the thing, okay? Now here comes to this is explanation here, okay? Now here I think it's very trivial. Is the mean is just N times P, okay? Because N success, right? Suppose you told 10 coin, which is fair. How many head you expect? 5. Half of them is head, half of them tail, right? 10 times 1/2 is 5, right? You roll 4 coin, you expect 2 of them are head, right? And the variance, do note that is a little bit tricky because independent is not N squared, so that's N, okay? The variance are N, okay? Now, before we let you go, let you see this graph and example. So N is 6, P is 5, 0.5 is symmetric. If P is 0.3 is less, it's going to be looped on the left-hand side. So here, see the last example will end today here. So this example that is application, as I promised, okay? So the restaurant owner, he know that 30% of customer like spicy food. How you get 30%? From data, historically. The question is, you want to know what's probably 5 of customer who came exactly 2 like spicy food, okay? And that is the binomial x equal 2, okay? And just to remember why the formula like this is, go back to apply. I'll just write down here is NCX P of X 1 minus P N minus X. N is 5, X is 3, and P is 0.3, okay? So probably you ask why I need this calculated probability, right? You want to calculate X equal to 2, right? And also calculate X equal to 0 and X equal to 1, right? And add up how much of them, then you need to decide how many spicy food you need to prepare, right? If probably 2 or less than 2, it's not a lot, then probably just prepare 2 customers spicy food, right? And then you would be able to satisfy most of their want, right? That is how you do probably modeling, right? You assume there's certain kind of underlying what's going on, and then you can derive the answer to do decision making, right? You can see whether you need to prepare 3 customer serving or 2 or 1, depend on what is the cutoff, right? And then it means how many food you need to prepare, okay? Is that okay? Is that clear what we're doing? Don't worry, we'll talk about this next class. Enjoy your weekend. Happy